few more problems on calorimetry. So this one, the next one that I'm talking of, is a copper calorimeter whose mass is 100 grams and one that contains 200 grams of water at 50 degrees centigrade. All right. Next, what is done is there is a piece of ice of mass 20 grams at minus 5 degrees centigrade that is dropped into the calorimeter. What is going to be the final result? What would be the final outcome? Means what would be the final temperature of the unit? What's given is that the specific heat of copper is 0.1, for ice is 0.5, and the latent heat of fusion of ice is 80 calories per gram. Right? Now, first things first. So, the calorimeter along with its contents, right? Let's see how much heat it will release in cooling to 0 degrees centigrade. How much heat is it going to release when it cools to 0 degrees centigrade? So in cooling to 0 degrees centigrade, there is like 100 grams of calorimeter, copper, 100 grams of copper, specific heat 0.1 into 50 degrees. From 50 to 0 is decrease of temperature 50. And then for water, mass into specific heat 1 into 50. That's for water. These many calories to cool to 0 degrees centigrade. 10,500 calories it's going to release when it has to cool to 0 degrees centigrade. Now, there is ice at minus 5 degrees centigrade, 20 grams of ice at minus 5 degrees centigrade. Let's see how much heat would be required. How much heat would be required for 20 grams of ice to get converted into 20 grams of water at 0 degrees centigrade. So what are the two things involved here? 20 grams of ice at minus 5 degrees will take sensible heat to get converted into 20 grams of water at 0 degrees centigrade. And 20 grams of water then at 0 degrees centigrade, will 20 grams of ice at minus 5 degrees centigrade will get converted into 20 grams of ice at 0 degrees centigrade. That's sensible heat. And then I have 20 grams of ice at 0 degrees centigrade that would assimilate latent heat to get converted into 20 grams of water at 0 degrees centigrade. So 20 grams of ice at minus 5 degrees centigrade to 20 grams of water at 0 degrees centigrade. It involves two things. One, sensible heat from minus 5 to 0, and then at 0 there is change of state, so there is latent heat involved. Let's see the total amount of heat participation for this process. So 20 grams of ice of specific heat 0.5, and its temperature rises from minus 5 to 0. Mass into specific heat into rise of temperature. So that's a sensible heat component. And then 20 grams of ice at 0 degrees centigrade to 20 grams of water at 0 degrees centigrade is going to be 20 into 80 calories. So that makes a total of 1650 calories. Very clearly, the amount of heat released by the calorimeter is a lot more than what would be required to completely melt ice that was originally at minus 5 degrees centigrade. So the common final temperature would be greater than 0 degrees centigrade. Let's say theta is the common final temperature, right? So then, what's the heat lost by the calorimeter? Mass of the calorimeter into 0.1, its specific heat, into decrease of temperature, which is 50 minus theta. It was originally at 50 and theta is the final common temperature. Then there is like 200 grams of water into specific heat 1 into fall of temperature 50 minus theta. So that's the heat lost by the calorimeter and its content. And where does it go? To convert that into water at 0 degrees centigrade, which is 1650, which we have already computed, plus now I have 20 grams of water. Specific heat 1. From 0 degrees to theta degrees, the heat participation would be mass specific heat into theta. This is my equation. Heat lost is heat gain. And then when I solve for theta, theta turns out to be 38.48 degrees centigrade. Yes or no? Right? Let's look at another problem. Let's look at another problem in the context. So we have now a piece of metal of mass 10 grams, right? There is a metallic piece of mass 10 grams. And it's heated to 100 degrees centigrade. It's heated to 100 degrees centigrade. And then dropped in a mixture of water and ice. Then dropped in a mixture of water and ice. The volume of this mixture decreased by 0.1 cc. The volume of this mixture decreased by 0.1 cc. Though the temperature remained the same. Now that's interesting. Which means what? You know, this metallic piece that was at 100 degrees centigrade, when it released heat, it did not result in increase of temperature of the water and ice. That means all the heat that was released was just about used to melt part of the ice, because until and unless, so water will not take latent heat to increase its temperature. First, the ice component will melt. So some part of the ice would have melted, right? So until and unless the entire ice melts, and we have water at 0 degrees centigrade, there would be no sensible heating. There is going to be no increase of temperature. So first, let's see that the heat released by this. So one thing, the initial temperature of the mixture was 0 degrees centigrade. Final temperature is also 0 degrees centigrade. That means the final temperature of the metallic piece is also 0 degrees centigrade. That means how much of heat is lost by the metallic piece? The metallic piece, 10 grams mass into specific heat into change of temperature. That's the heat lost by the metallic piece, right? Now come to the ice. That must be mass of the ice, which we have to compute into the latent heat. So I have to compute the mass of ice that has got melted by this amount of heat, right? So it's given density of ice is 0.916 grams per cc. Density of water is 1 gram per cc. So realize that density of ice is less than density of water at 0 degrees centigrade. So if density of ice is less than density of water, then what happens when ice gets converted into water at 0 degrees? When ice at 0 degrees centigrade gets converted into water at 0 degrees centigrade, what happens? What happens to the volume? What happens to the volume? See, from ice to water, there is increase in density, 0.916 to 1 gram for the same mass, right? There is increase in density. If there is increase in density, there must be a decrease in volume. That means when ice melts, there is contraction. When ice melts, there must be contraction, right? For every gram of ice, how much of contraction takes place? If I have 1 gram of ice, how much of contraction takes place? For 1 gram of ice, the amount of the volume of ice would be mass. The volume of ice is going to be mass divided by its density, 0.916. That's the volume of ice. But that 1 gram gets converted into water. It will produce 1 cc of water. So what's the decrease in volume from ice to water? 1 by 0.916, that was the volume of ice for 1 gram. And 1 gram of water was 1 cc. So that's a decrease in volume. So now what they say is that there is a total decrease in volume of 0.1 cc. So decrease in 0.1 cc divided by these many cc's per gram. This is the cc per gram of ice. 0.1 cc was the decrease in volume divided by decrease in volume per unit mass of ice. Decrease in volume per gram of ice. This is decrease in volume per gram of ice. If you divide this by this, you get grams of ice. Divide this by this, you get 1.09 grams of ice. So now, heat loss by the metal must have got entirely consumed by 1.09 grams of ice to get at 0 degrees centigrade to get converted into water at 0 degrees centigrade. So there is latent heat participation from that end. So heat loss by the metal, mass into specific heat into 100 minus 0. Its original temperature was 100. Its final temperature is 0. So that's the heat loss by the metal. That must be mass of ice, which we have computed out of the contraction that took place in the volume, right? 1.09 into latent heat. And when you solve for S turns out to be 0.087 calories per gram. Yes or no? I hope you're feeling comfortable. More with a few more problems in a little while. Bye-bye.